So what we've looked at so far are simple molecules in which you have a central atom, and there are a lot of molecules actually which are not simple, do not have a central atom, such as these molecules, for example, cysteine, which is found in your body, ibuprofen, which you take when you have bodily pain, methylamine, and then everyday compounds such as acetone and isopropanol, written here as 2-propanol. So all of these compounds are all polar, okay? So you can see from the ball and stick models, you have some electronegative atoms like sulfur. You also have oxygens and nitrogens, which the dipoles of which, with the bonds that they form with another atom, are not cancelled out by another similar bond pointing in the opposite direction. And more of these are actually found in your body. Okay, like for example, in the form of proteins, these are the bonds which are formed in proteins. And again, it is because of these geometries that proteins are actually stabilized in your body. Okay, but I'd like to move on forward now with the valence bond theory. Okay, so the VSEPR model is actually great in a sense that it predicts the overall shape of molecules, and it's pretty good at that job. But it doesn't really explain at the scientific or at the molecular level why there are bonds existing between atoms. And the valence bond theory, we will not go into too much detail for that. It's just a simple model which says that covalent bonds are formed when you have orbitals overlapping. So remember that we have defined in chapter 2 an orbital to be characterized by an N, L, and M sub L value. Okay, so if you have those orbitals overlapping each other, then you form a covalent bond. Let's say, for example, if you have two 1s orbitals, one from each hydrogen atom, if they overlap, since each of those 1s orbitals hold one electron each, then you have the hydrogen molecule, H2. Okay, now if you have a head-on overlap, then the bond formed between these two 1s molecules, or these two 1s orbitals, is actually called a sigma bond. Okay, so this is a sigma bond. Okay, and again, a sigma bond is always a head-on overlap of two atomic orbitals. Okay, now when these, or well, rather, another example will be if you have fluorine. Okay, fluorine 2p, which has 7 valence electrons. Okay, remember. And then you have another fluorine with 7 valence electrons. When they actually overlap each other, then you will have yet another sigma bond. Okay, but notice that in this cartoon you can still distinguish one 2p bond from the other. This blue region here, by the way, just denotes like an air quote negative part of the 2p orbital. So it really has nothing to do that much with our discussion, at least at this point. And this valence bond theory also applies for different atoms. Let's say, for example, if you have hydrogen and chlorine. So here, this is the head-on overlap of a 1s orbital and a 3p orbital. Okay, and again, the formation of those, the overlap results in the formation of this sigma bond. Okay, and basically you can still see, or you can still distinguish rather the 3p orbital from chlorine and the 1s orbital from hydrogen. Okay, one concept here it says is that the greater the orbital overlap, the stronger the bond. So this just means that if, for example, you have, let's say, considering hydrogen chloride, and let's say, for example, we have hydrogen bromide. Okay, so hydrogen bromide will overlap with the 1s, or rather the 4p orbital of hydrogen, or of bromine, will overlap with the 1s of hydrogen. And what will look, it will look something like this. okay, and I'm going to exaggerate this a little bit, okay. So the 4p orbital, okay, 4p orbital from hydrogen bromide, that should be of the same shape-ish, just pretend. So if this is hydrogen bromide and then this is 1s, since the 4p orbital is much greater in size, okay, the 4p orbital is greater in size than the 3p orbital, there's only less overlap between these two orbitals, 1s and 4p. So the hydrogen bromide bond, or this hydrogen Br bond, is actually much weaker than the hydrogen chlorine bond. Okay, but what if, for example, you have molecules with more than 2 atoms? We've only considered here molecules of 2 atoms, so basically diatomic molecules. Now together, the valence bond theory and the VSEPR theory actually provide quite a good darn job of predicting the overall shape of molecules, and at the same time how those bonds are formed between atoms in the molecules. However, it does not really give any relationship to the filling and shapes of those atomic orbitals. Let's say, for example, as we will see later, CH4 or methane, which has 4 equal CH bonds. If we only use the valence bond electron theory and the VSEPR theory, then we cannot actually explain why those 4 bonds are equal. And for this, we need another theory, the hybridization theory. Okay, so let us again look at the hybridization theory. Or rather, let's look again at methane. So what I was talking about is if you were to form a methane molecule, so you need basically 4 hydrogens, okay, to overlap with orbitals from carbon, and 4 of them should basically be involved. Okay, so for hydrogen, that's just for 1s orbitals, okay. Now for carbon, it has 4 valence electrons, in particular at 2s and 2p. 2 of those valence electrons are in 2s and 2 of them are in 2p. Now if this were the case, notice that these 2 electrons in 2s are actually paired, and that just means that they cannot really form a bond. But as we know, methane does exist, CH4, and carbon can actually form 4 bonds with another atom, okay? But if there are only 2 available, then what's basically incorrect, or what are we missing? So let's say, for example, let's do a thought experiment. Say, for example, let's promote one of these electrons from 2s into 2p, okay? If we promote it to that empty 2p orbital, then we will have this electron configuration for carbon. Now it has 4 available valence electrons for bonding, but there's still a problem with this one because the 2s orbital is not actually equal, let's say, for example, in energy and in shape to the 2p orbital, okay? So that will mean, given this, what we have right now, if carbon were to form 4 bonds, then 3 of those bonds are only equal, and one of the bond is actually not equal to those 3. But that's not what experimentation shows. All of those bonds are actually equal. That's why we can also assume that methane is nonpolar. So what's actually missing with this one? So what's missing here is, again, the fact that you now have 4 unpaired electrons, but they're not equal. They're not going to form 4 equal bonds just because different orbitals, or there are 2 different types of orbitals. But if we do another thought experiment in which we assume that maybe all of those 4 electrons are in hybrid orbitals, okay, hybrid orbitals, or a new orbital which basically will have this configuration, sp3, This new orbital, let's say, is a mix of 2s and 2s and 3p orbitals, okay? And this hybrid orbital, let's assume that it has 4 orbitals, and basically these orbitals 1, 2, 3, and 4 are actually equal to each other. Then these electrons, these valence electrons, will now then form equal bonds when it forms bonds with 4 atoms of the same element. Let's say, for example, again, hydrogen from methane. Okay, so this is what an sp3 hybrid orbital looks like. Okay, so again, an sp3 hybrid orbital is composed of 4 orbitals. S is 1 plus 3. Okay, 1 plus 3 is equal to 4. Okay, the sp3 orbital has actually 4 different orientations as shown in this cartoon, but again, the sp3 comes from the fact that it is formed from 1 s orbital and 3 p orbitals. Okay, anything with a tetrahedral electron pair geometry should be sp3 hybridized. So for example, the nitrogen in ammonia and the oxygen in water, both of them are also sp3 hybridized. Let's consider here ethane, a molecule which has the formula C2H6 and does not contain a central atom. Shown here is that when sp3 orbitals from one carbon and another sp3 orbital from another carbon overlap each other, so they will actually form an sp3 sigma bond, and this bond is actually this single bond. The sigma bond is the single bond. Okay,